Hello and welcome back. We get interrupted many times in a day. For example, whilst watching this video, if you heard any beep, tone, or sound from your mobile phone, chances are high that you will stop watching this video for a brief moment. Check your phone to see why that tone came in. It could be an email, it could be a WhatsApp message, it could be a message you've been waiting for, or any other event at all that demands your attention. And after you have attended to this interruption by your phone, you will come back to this video and you continue from where you left off. Now, some things are important here. You realize that when you heard the beep on your phone, your attention immediately switched from the video you were watching, and then you went back to check your phone. And then when you came, you probably paused, right? So you pause the video first in many cases, and then you go to check your phone, you come back to the video, and then you continue playing from where you left off. Something similar happens in a microcontroller. And not surprisingly, it is called interrupt. So, this video is about understanding interrupt and how to write code that uses interrupt to get the CPU to respond to events instead of constantly checking in a while loop like we did in the previous video. So, what is an interrupt within the context of a CPU? An interrupt is any event that triggers the CPU to stop whatever it is doing at the moment. It takes note of what it was doing. It takes a state, like it takes a record of the state of what it was doing at the moment when the interruption came in. And then it will go to attend to that interrupt. Now, the thing or the code that is executed in response to an interrupt is called an interrupt service routine, or an ISR. Very soon I will explain the code you are seeing here, and then you will know which one is the ISR. But if you have paid attention, you realize that I have an ISR here, so you already know this is the ISR that I'm talking about. So an interrupt service routine is basically a function that your CPU will execute in response to an interrupt. One key thing about ISRs, or interrupt service routines, is that they shouldn't be time consuming. Why? Because the CPU left off from something that it was doing to come and attend to something that we think is of higher priority, right? So it will attend to this so-called higher priority task or function, and then when it finishes, it has to go back to continue what it was doing. Now let's see how we can implement interrupt in code. This code is just a modification of the previous code we used to detect button presses, and then we turned on an LED in response. The modification here has made this become a firmware that instead of constantly pulling, so you can see that, sorry, you can see that in this while loop, we are not constantly checking if a button has been pressed or not. Instead, an interrupt happens when the button is pressed, and then an ISR is executed in response. What the ISR is doing is to toggle the LED. So if it is on and I press, it will go off. If it is off and I press, it's going to come on. So I'm going to explain the code line by line so that you understand how to set up interrupt and interrupt service routines that should trigger when something happens through your GPIOs. However, before I do that, note that it is not only GPIOs that can trigger interrupt. As we talk about further peripherals in upcoming videos, you realize that USAT or UART can also trigger interrupt. Timers can trigger interrupt. your I2C devices can trigger interrupt. Your SPI devices can trigger interrupt. So the sources of interrupt can be either external or internal based on where it is coming from and what is causing it to happen. Now, let's focus on how to trigger interrupt when the state of a GPIO pin changes from either high to low or from low to high. So, line 7, line 8, you are familiar with them. We are basically loading the button and the LED based on the definitions in the device tree source. We have seen this multiple times. What is different here is on line 10, I have a variable called button CB data, and I mean button callback data, and the type is GPIO callback. We'll get to this very soon. And then outside of main, I have also defined a function called button pressed ISR. You don't necessarily have to include the ISR in the name. I have included it so that it is obvious that it is an interrupt service routine. However, you are free to call it whatever at all you want to call it. But you have to have the habit of making sure that your function names are descriptive enough so that people who read your code will immediately understand what the code is meant to do. Now, the signature of this function is mandatory. It is something that you have to follow if you want to set up an ISR. So I'm going to take time to explain to you what the individual parameters or arguments are for. In simple cases, they are almost practically useless, like we don't use them. But in situations where we have registered multiple interrupts on the same GPIO, but we don't want to create multiple interrupt service routines for each of these interrupt sources, then we can just have one ISR like I have here. And because of the parameters we pass to it, we can check the source of the interrupt and then react accordingly. Okay? So the first parameter here is construct device, and I am calling it dev. Again, you can choose any name for the variable names. It doesn't have to be what I have written here. This device type is something you are already familiar with. It is the generic device struct that we use to access peripherals that have been defined in the device tree, right? So this will help us to be able to distinguish, like we can write code to check, is this interrupt that happened, is it coming from GPIO A, GPIO B, GPIO C, if you're on an STM or any other platform that uses that naming scheme? Or is it coming from GPIO 0, GPIO 1, if you are on a platform like Nordic Semiconductors? So this device here will help you in the case of using a single interrupt service routine to handle multiple interrupt sources. Then you can check the source of this interrupt so that you take the appropriate action. In our case, it's not useful, it's not needed. But because that is the signature that the Zephyr platform requires, we have to make sure we match up to it. The next one is extract GPIO callback, and then I'm calling my own CB. It's a pointer, right? This is what actually links the interrupt to the interrupt source. And this is where a deeper understanding of the platform on which you are working or you are deploying your code comes to play. I will explain this using ARM-based microcontrollers. In ARM, there is something called ESTI, and it defines the sources of interrupt that comes into the GPIOs. One ESTI line can be shared by multiple GPIO ports and multiple GPIO pins. And the structure in your code that will help you to be able to traverse that connection is this GPIO callback. Usually, I encourage people to have the habit of control clicking to go into the definition of structs that you use to sort of understand what is going on in there, right? So this is the link between the interrupt source and the interrupt itself, right? And then the uint type pins here is just a bit mask that tells us the particular pin on which the interrupt event is happening. So again, you can see that all of these three parameters or arguments that are required by the interrupt service routine signature are there to help us in the situation when we have registered multiple interrupts. We'll see it in later videos. We have registered multiple interrupts and we just want to handle all of these interrupts with a single interrupt service routine. In our case, you can see that in the code here, we aren't using any of these parameters here at all. However, we can't omit them, so they have to be there. Now, I told you that this function, button pressed ISR, is the interrupt service routine that is invoked by the CPU when an interrupt happens on this button here. And this button is SW0 on my STM32F4 discovery. It could point to a different button depending on the kind of board that you are using. It doesn't matter. Now, what we are doing here is I don't even check anything. I just say GPIO pin toggle DT and then I tell it, I give it the LED. So basically I'm saying when I press the button, if the LED is already on, set it off. That's what toggling means. And if the LED is off, then turn it on. So I'm just toggling. So when I show you a video of myself playing with this firmware, you see that when I press, the button will come on if it was off, and then when I press again, it will go off if it was on. Now let's come to our main function. This int_ret is what we use to handle the returns of those functions that we'll be calling. Here we check if the button port is ready. You understand everything, so I do not need to explain any further. Here, I am configuring my button as a pull down. So what it means is that when you press the button, it should read a high instead of a low, because by default it is pulled down. So contrary to what you saw in the previous video where I made us look at bouncing of buttons on an oscilloscope, you saw that in that video, if I have not pressed the button, it reads a high 5 volt, and if I press, it reads a low. In this case, the setup of the button on my board, so here you have to modify the code to suit how the button is set on your board. But on my board, which is STM32F4 Discovery, the button is set up such that it is pulled to ground. So when I press, it becomes high, and that is how I can detect whether it has been pressed or not. So you understand everything up to line 36. Now let's go to line 38, which is very important and is something you haven't seen before. We are calling a function called GPIO pin configure, GPIO pin interrupt configure DT. There is the other variant, which is GPIO pin interrupt configure. And by now you realize that the DT ones comes to play when we are using GPIO DT spec. But if we just use the device generic, then we don't have to add DT here. And the function signature is also a bit different. So now we say we are configuring an interrupt for the button. This one is a flag. So let me hover here and then let's see what it takes. Yes. So you can see the function signature. It's expected GPIO DT spec, which we have, and then GPIO flags type. And the flags type is basically we are telling it on what event should the interrupt be triggered. So here we say GPIO interrupt edge rising. Remember, our button is set up as a pull down. So when it is not pressed, it is reading 0. Now when we press it, it will rise from 0 to whatever the VDD or the VCC, the supply voltage of your board is. And that is called a rising edge because it is rising from 0 to some set voltage. So we are telling our firmware that, see, notify the CPU whenever you realize that whichever pin, GPIO pin, this button is hooked to, moves from a low voltage level and it is going to a high voltage level. So this is what happens when we press the button. So what it means is the CPU is not bothered for as long as we have not pressed the button. The moment we press the button, the CPU will be signaled. There are other peripherals on ARM systems. It's called NVIC or NVIC. All right, nested vector interrupt controller, and it could be called something else on other platforms. I do not want to descend so low into the details of a specific platform, so I'm keeping myself at this level. But basically, when you press the button, something happens in the hardware that is able to notify the CPU that, dude, you are supposed to react to this event that has happened because it is somewhere registered in the firmware that you are running. The question is, how do we register this? But before I answer that, similar to most calls, it returns an integer, and if it is negative, it means that setup failed, so we return here, right? Now, line 43, I'm calling a function called GPIO init callback. And then you can see that I'm passing button CB data, which is the callback data we declared up here. And then I'm also telling it which interrupt service routine should be run. So here I say button pressed ISR. And then see bit button.pin. Remember I told you that this is a bit mask that tells us the particular pin that is triggering the interrupt. So with this code here, we are able to indicate to the interrupt service routine that this particular pin, the button's pin, is the one that was pressed. So if anywhere in this code we check for this particular pins to know which pin was pressed, again, remember, it becomes important when there are multiple interrupts being handled by a single interrupt service routine. This is not the case in this situation, so it doesn't matter. Now, we have initialized our callback. And then what happens? We need to now register the callback. This is the point where we are registering. So we say GPIO add callback DT button and then button CB data. So this with these two lines of code coupled with what is here, we are basically telling our CPU that, dude, continue to do whatever you are doing, but the moment you get the signal that the button is changing state from a low state heading to a high state, then go and execute this function called button pressed ISR. So whatever code is in there is going to happen. So look at what happens here. In our while loop, we are basically just using this MS Sleep 500 to simulate the situation where the CPU might be busy doing something else, right? So in this while loop, we could do anything at all, anything. Think of it this way, like a lift, for example. Let's say your firmware is controlling a lift. The interrupt here could be when you press, so you're standing on level 2 and the lift at the moment is below ground, so let's say -2, and you are at level 2 above ground. If you press, an interrupt happens in the firmware of the lift, and at that point the most important thing the lift has to do is to come to the level where the interrupt occurred, and some way somehow the firmware will know that you are standing at level 2, and so it will have to trigger the mechanisms that will be needed to lift it up to level 2 so you can enter. This is basically all you have to know about interrupt and how to set them up. I believe I've done a good work explaining this, and it's time for you to see it at work. Now, before I show you the working firmware on the board, keep in mind that just because we are using interrupt doesn't mean it automatically takes care of switch debouncing. No. So the same problem that we saw in the previous video where the transitioning between low and high isn't instantaneous and isn't smooth, it also happens with interrupt because it's a problem of the button. Has nothing to do with your firmware, has nothing to do with the board itself. It's a problem with mechanical switches. So this the use of interrupt doesn't take away the fact that you need to guard against switch bouncing using a debouncing technique. I gave it to you as an assignment previously. In another video, I will show you how to take care of switch debouncing in code. Now, I'm going to switch to a place where you can see me. Then I'm going to play with the firmware right here. So this is the user button. I press it once. You see that the LED has come on. Then I press it again. It goes off. I press it. It comes on. I press it. It goes off. If we play with this long enough, we will start seeing switch bouncing at play. Like see, okay, now it's not happening. But sometimes you will press and it wouldn't do what you expect it to do. So I'm telling you this so that you do not assume that because I'm using interrupt, switch bouncing. You saw it happen right there. You see. So it doesn't automatically take care of the need for you to implement a debouncing technique in your code. This is it for interrupt. Thank you very much for watching, and I will see you in the next video.